Our next speaker is Shilei Tian, who cannot join us on site, but remotely. Shilei, are you there?
Yes, I'm there. Can you hear me?
Yes.
Can I share my screen? Because currently I can't see. Yeah. Oh, okay.
Can you now?
Yeah. Let me try. Can you see my screen now?
Yes, we can.
Okay, full screen mode, right? Oh, okay.
Okay. Cool. Yeah, Joseph is here saying you are not doing your presentation alone, but with Joseph together. Shilei, you're starting with the presentation?
Yeah, I will start with that.
So let's present. So joining us is Shilei Tian from the University of Stony Brook and Joseph Huber from recently changed to AMD now, who are going to present us about just-in-time compilation and LTO using for OpenMP target offloading. Shilei, your turn.
Thanks. Hi, I'm Shilei. I'm a PhD student at Stony Brook University, supervised by Dr. Barbara Chapman. Today, Joseph from AMD, who also attends in person, and I are going to talk about our work, just-in-time compilation and link time optimization for OpenMP target offloading, which was collaborated with John from Oregon National Lab and Johannes from Lawrence Livermore National Lab. Actually, like Michael mentioned, I'm also actually in Chattanooga, just 1 mile from the conference center. But because I'm in close contact with a COVID-19 patient, I think it's better for everyone that I'm self-quarantining. Okay, here is the outline of today's talk. First, I will introduce our motivation, and then Joseph will introduce a new offloading driver and how we built LTO on top of that. Next, I will talk about our just-in-time compilation support and finally discuss the future work. Let's say we have an OpenMP target offloading program and we want it to run on a NVIDIA A100 GPU. It contains 2 source files, foo.c and bar.c. When we compile it, we first compile foo.c. The compilation has 2 passes, and the host code and device code will be bundled together. Next, we compile another file, bar.c, the same procedure, basically. And after we get the 2 object files, we link them together. And at runtime initialization stage, the device image will be loaded to the device, and we get the target table, which can be used later when we launch a kernel. The process we introduced above has some limitations. First, when we compile the program, we have to specify the sub-architecture. That is because device binaries for different sub-architectures are not compatible. Second, compiler can only see 1 translation unit when optimizing the code. If we have function calls across translation units, we can't do too much optimization with that. And lastly, no matter how smart a compiler is, there is always information not available at compile time, preventing the compiler from optimizing the code further. Just-in-time compilation is usually one way to deal with the portability limitation. Actually, many heterogeneous programming languages support JIT compilation. OpenCL's SQL support JIT intrinsically. CUDA support JIT compilation in some sense. Basically, they just call PTXAS at runtime. In addition to portability, performance is another aspect because now we have those information only available at runtime. For the second limitation, link time optimization is widely used because at link time, we can see code from all translation units. In this work, we bring LTO and JIT to LVM OpenMP. In order to do it, we implemented a new compiler driver, offloading driver, and a new augmented linker supporting OpenMP offloading compilation in a unified manner, which will be introduced by Joseph next. We also implemented a new JIT runtime system supporting generating device code at runtime. Now I'm going to hand it over to Joseph.
Okay, thank you, Shilei. So Like he said, the old offloading driver had some major issues that actually prevented us from correctly supporting like LTO and JIT in the device. So if you look at this general overview of the compilation flow for the old, now completely removed driver in upstream Clang, we would first take all the sources, do the host and the device code gen, and then use an explicit like bundler application to create a fat binary. This, during link time, would then be fed back into Clang, and the Clang driver would then do the extraction and linking of the device phases, and then additionally a wrapper phase, which created the registration code and the device image that Shilei showed earlier. And this has many problems for actually supporting things like LTO or even static libraries like Johannes mentioned in his talk, because we're basically forcing the Clang driver to behave like a linker, when the Clang driver doesn't really have a complete view of what is in these files, like if it contains bitcode for LTO or object codes, or even like what the user's linker paths are. So we can't know like, oh, is this a static library with or without device code? So previously, because of this like bundler and unbundling interface done by the Clang driver itself, we pretty much just had to guess. So in order for you to successfully compile your program, you had to make sure that all of your triples and your arguments were given the exact same and in the exact same order for the compilation and for the linking phase. And that made it very difficult to support, LTO. So next slide, please. And another problem was that this had, fundamentally different phases used for NVIDIA and AMD or even like x86 offloading. And that resulted in like tremendously complicated code inside the Clang driver that was, thousands of lines of just repeating boilerplate just for like the slight differences for this linking architecture versus this, And also, like I said, we were treating the freaking driver as a linker, and that wasn't very good. So the solution here, before supporting LTO, we wanted LTO to work, but then we kind of realized it wouldn't work with the current framework. So we ended up needing to completely rework the driver into something new, and that, had a lot of other benefits that Johannes mentioned in his talk. So next slide, please. So this is just a very short overview of the new compilation flow. As before, we'll take a source file like foo.c and run the host and the device compilers on it separately. So we'll first create the host bitcode output, and then we'll create the device object output. And the reason we create the host bitcode object first is one, so we can read it to make sure that the kernels on the device and host match their names so we can register them correctly. And then once we create the device object, we embed it directly into the host bitcode as like an LLVM global. So we don't need that explicit bundler phase that creates a like dependency between the host and the device in one phase. And then once we have that, we get the host bitcode file and we just run it through the host compiler to get the final object file. And this is our new fat binary that just contains some device code that we can then read later. So next slide, please. So if you look into that device compilation phase, it's actually a collection of different phases using like vendor tools like PTXAS and the LLVM front end and back end. And we'll touch on this later when we get to LTO. But right now, this is the standard compilation flow to create relocatable objects that can be linked together. Okay, next slide, please. Now, the main difference in the new driver versus what I mentioned previously in the old driver is that all of the linking is done in a linker. And in this case, it's called the linker wrapper, which is basically you take the host's linker and you put that inside of another program that does the offloading linking portion. So we'll take the inputs and extract the device inputs out of them. In this case, we have foo.o and bar.o being examples of codes that could have offloading code in them. And for example, you don't even need to specify offload arch here in the compiler invocation. That's one advantage of it. But anyway, you extract the device code, you see all the device codes that's in there, so it's reactive to what's in the object rather than prescriptively saying, I know there's going to be this many architectures in this order with this triple, and then we can just link together whatever needs to be linked, get the linked device image, send it through the wrapper, which creates the registration code, and then we just feed that in with the other host inputs to create the final offloading executable. And this let us go, yeah, you can go for it. And now that we had this new framework, it was actually very, very easy to support link time optimization. So, and all that we need to do here is that instead of creating that, object file, before we just specify -f offload LTO, and that tells the compiler to not generate the device object file, we just generate a bitcode file. Then we embed that in the same way we did before, and we can just send it to the linker wrapper. So next slide, please. And that, now you can see that we've basically gotten rid of all the PTXAS calls and whatnot, and we just end up with the device bitcode file that gets embedded. Next slide. Now, when you go into the linker wrapper will extract these device inputs and see that, oh, hey, this is a bitcode file, and it will add it to a list of inputs that will then be sent to LLVM's LTO library. So all we need to do is take all of the bitcode files and then link them with LTO and optimize them. We get out our, PTX file. We run it through PTAX again in the linker wrapper. We get our final binary, and then we just do the wrapping and embedding as before. And that was only a few changes to actually support LTO with this new scheme, and it gives a lot of benefits. So next slide, please. So we did a brief evaluation on a NVIDIA A100 GPU using a baseline LLVM at the time. And what we tested were 3 main applications: OpenMC, Thermal 4PFM, and Mini MDoc, and some proxy applications: XS Bench, RS Bench, SU3, and Mini FMMM. And the main distinction here between the applications and the proxy apps is the applications are all large, multi-file programs. So they actually benefit primarily from the LTO, whereas the proxy apps are all like single translation unit programs. Next slide, please. So this is the performance results we saw from enabling LTO for these applications and proxy apps on that A100 GPU. So you can see in the general case, even for the single TU applications like XS Bench and RS Bench, we got either the same or better performance through LTO, even though there should theoretically be no benefit from cross-module linking. And that's primarily because LTO runs the optimizations, runs more optimization, since we're basically doing 2 phases, and that can sometimes, get rid of some extra things. And also because we do LTO, even if it's like a single TU, certain variables that may or may not have been like weak or some other kind of weird linkage, because even if it's 1 TU, we can say, oh, hey, I only have 1 translation unit, turn that weak to an internal variable. So that's sometimes where you can see performance benefits even in a single translation unit. We had some performance degradation in Mini FMM. I think that was primarily due to some change in like inlining. I don't remember exactly what that was, but the main thing to look at is the last 3 applications had, up to from 1.5 to 4x performance increases just from being able to inline everything between the modules. So LTO is very good for, these applications, especially with OpenMP, which encourages this, multi-TU approach. So that's it. So I'm going to hand it back over to Shilei, who will talk about the just-in-time compilation, which basically builds on top of the LTO support that I just mentioned.
Yeah, thanks, Joseph. Now I will talk about the just-in-time compilation. The compilation flow of JIT is built on top of the new offloading driver and LTO Joseph just introduced. And extra compiler flag offload JIT is added. Internally, inside the linker wrapper, after LTO, the compilation basically just stops at generating LLVM bitcode and then embeds it into the wrapper. All the remaining steps are the same. Now at runtime, during the initialization, since we have the LLVM bitcode instead of a device image, before loading it to the device, we need to run the LLVM backend. Now that we know the actual device, we can generate the corresponding image thus solve the portability issue we mentioned before. Now that we are done with our implementation, let's move to evaluation. Well, actually, no, it's not good enough. As we mentioned, we also have the runtime information when we launch a kernel, such as all the kernel arguments and whether the user specifies the number of teams and so on. They can help optimize the code further. Okay, let's move the code generation stuff to kernel launch time and use the runtime information. Internally, it will work like this. First, we create an LVM LTO module from the embedded LVM bit code, and then update the module based on the runtime information. I will talk about what information we use and how we update the module later. Next, the module is fed to LTO code gen, which is created based on the device, the actual device. Then will be optimization and code generation, and we will get the assembly. After we call the vendor toolchain to generate the image, which might be optional depending on the actual target. We load it to the device and launch the kernel. Okay, now we use the runtime information. Potentially, we can get better kernel performance. We are good now, right? Well, still not exactly. There is still an issue. But before we discuss it, let's first look at how we use the runtime information. I will use this simple CUDA kernel launch as an example. When we launch a kernel, we know that the kernel function, of course, launching parameters and kernel arguments. Here we have three arguments, an integer, a pointer, and a floating point value. Since we have already know those values, we could use them to update the kernel function. Specifically, for the scalar argument, we replace it with the actual runtime value. For the pointer argument, using the actual value doesn't make too much sense. Instead, we specify the actual pointer alignment of the argument. The benefit is that even though every backend has its default alignment, the actual alignment is usually much stricter, potentially giving us better vectorization and so on. In addition, in the code, there are always function calls to query how many teams and how many threads in a team. Since we have those information, we can directly replace those function calls with the actual values. At last, we only keep code related to that kernel launch, and all the other code will be removed. In that way, it could help reduce the image size. Now, let's see. We have two kernel launches. When the first one is launched, we go through all the steps in the JIT engine, basically get the image loaded to the device, get the target table, and launch it. So far, so good. Next, we have the second kernel launch this time. Everything regarding the launch is same as before. Same kernel, of course, same launching parameters, same kernel arguments. Do we still have to go through the JIT engine again? Or generally speaking, do we have to JIT the image every time when we have a kernel launch? We definitely want to reuse previous target tables as much as possible because all the steps have overhead. Here, the second kernel launch is identical to the previous one, to the first one. It can directly use the target table of the first launch. But what about this one? The pointer argument is not the same as before. However, the two pointers are both aligned to 16, which means the first image or the first generated target table also works for the second kernel launch. So basically, we need a way to identify each kernel launch and see if there is already an image that works for it, such that we can directly reuse it without JITting a new one. In our work, we propose kernel launch descriptor, which consists of all the factors we mentioned before. If two descriptors are compatible, they can use the same image or the same target table. Two kernel launches are compatible if, for scalar values, they have to be exactly the same. For pointer values, they are same if their alignments are same. Okay, since we can identify kernel launch now, we add a cache to JIT engine. When a kernel is launched, a descriptor will be created first. Then that descriptor will be used to check if there is already a compatible image loaded to the device. If yes, use that directly and launch the kernel. If not, JIT the image loaded to the device, get the target table, put it into the cache for later use, and launch the kernel. However, this is still good enough. If we run an application multiple times, even if we have a cache, we still have to JIT the image in each run, at least once for the first run, right? Because the image already loaded to the device are only valid for that specific run. In fact, scientific applications tend to have similar execution patterns, which means the image generated in prior run are very likely to be reused. Given that fact, we introduce another level of cache. L1 cache is the first one we mentioned before. If L1 cache miss, we will check if we already have a compatible image. If yes, we can directly load it to the device, get the target table, put it into L1 cache, and launch it. If not, JIT the image, add it to L2 cache, and the rest are the same. When the application exits, all cached images are written into a file. When the application is initialized next time, those images are read from the file and loaded to L2 cache. So with a two-level caching system, are we good now? Well, almost. Let's look at this case. Here we have 3 kernel launches, but every time only the last argument is different. The rest are same. Even though we have the two-level caching system, we still have to JIT 3 images. That is, there is actually one benchmark in Spec Excel. If I'm not mistaken, it is 552 PEP. It has about 1,000 kernel launches, and the only difference is one of the scalar kernel arguments. Therefore, we end up with JITting 1,000 images and loading all of them to the device, which causes a huge overhead. In order to solve this, we introduce a specialization tracker. It basically tracks how many times each argument has been specialized, and also the total number of specializations we already have. If anyone has been specialized too many times, it will not be specialized anymore. Here is an example. We already have 3 specializations, and the third argument has been specialized all the time. Now we have another kernel launch. Still, the last argument is different. Instead of keeping specializing the third argument, we just skip it. And now we have another new kernel launch, and still the only difference is the lost argument. The image generated, however, the image generated for the previous kernel launch must be compatible because we skipped the specialization for the lost argument, and we can directly use that. Now put things together. This figure shows the full design of our JIT system. When the kernel is launched, a descriptor will be created first. Then we check if there is already a compatible target table, which means a compatible device image that has already been loaded to the device. If yes, we launch the kernel, and we are done. If not, we then check if there is already a compatible device image generated in previous run. If yes, load it to the device, get the target table, store it in the L1 cache, and launch the kernel. If not, JIT the image using the device and runtime information guided by the specialization tracker. Once we get the image, we do the same procedure we mentioned before. Now we are done. Let's take a look at the evaluation. We use the same configuration as LTO Joseph introduced before. Moreover, we also use an AMD MI100 system to test the portability. This figure shows the kernel execution time relative to the base ahead of time compilation. The LTO part has been already covered, so let's just focus on the JIT part. As we can see, in almost all the cases, JIT can improve the performance further compared with LTO. That is expected because because of all the specialization we introduced. This figure shows the end-to-end execution time relative to the base ahead of time compilation. The JIT version here doesn't use the L2 cache, and the JIT cache version here enables the L2 cache. End-to-end execution time contains the kernel execution time and all the overhead on the host, including the overhead to JITing the device image. This comparison demonstrates the performance improvement versus host-side overhead and how we can benefit from it after we finish the first run. We can see in most cases, even the JIT version without using offline cache or the L2 cache can improve the performance. That is because the overall performance improvement in kernel execution time is still more than the overhead from JITing the image. Using L2 cache can save more end-to-end execution time because we just reuse those images from prior run. Mini mdoc here still has performance degradation because there is one kernel argument that is randomly generated. Even with caches, it can be easily invalidated. And therefore, performance improvement in kernel execution cannot make up for the overhead of JITing. For thermal 4 PFM, as we can see, using L2 cache can help make up for the extra overhead of JITing images. We also test the portability using A100 and M100 GPUs whose sub-architecture is SM80 and GFX 908 respectively. We compile each benchmark using different sub-architectures and run them on the two GPUs. All the benchmarks can run without any problem. In the future, we would like to propose more optimization instead of just some specialization. We also want to provide portability beyond vendors. Currently, we embed LVMIR, which is target dependent. We still cannot have an application compiled for AMD GPU, but run on NVIDIA GPU. To solve that, we could potentially use some generic IR module and only link the target dependent code at JIT time. That's all. Thanks.
So thank you to the speakers from my side. I see there's one question. Think of more.
Nice work, guys. So the thing that occurs to me is that it seems like there might be some opportunity for extensions that could help guide the link time optimization. Like I look at the mini mdoc result, right? And I can imagine, say, kernels that are used for initialization and bringing data over to the device, but they're not getting executed repeatedly. So, and the user probably knows these things, right? So I'm just wondering if you've thought about that kind of extension or other extensions where the user could add an annotation that says something, useful, like execution frequency or randomness of the input or things like that.
Yeah, so actually we have an environment variable to enable the specialization or not, or just to enable part of the specialization we introduced. So definitely if user knows, okay, we know that part, it's just frequently changed. So don't do that, then we can just skip that.
So the environment variable can be specific, because this would be like on a directive by directive basis, and you could actually specify what parts, or even in the one where you said, okay, the input value is changing basically every time. You still want to specialize it, but not for that variable, right?
Right. You are right. Yeah.
So I'm just thinking that you could get more information from the user that could tell you, what's going, what changes, what doesn't change in some way.
Yeah, right. Yeah.
So there's two parts here. and then the two parts have, subparts and things left and right that, get complicated at some point. What if this is available to people and what isn't? And the parts about what isn't available, when will they be?
So
the
yeah,
LTO is available right now, and Shilei will talk about the JIT.
yeah, the JIT part has not been upstreamed yet. So I'm working on the upstream. So I hope we will have those JIT stuff soon.
Hi, Shilei. Thanks. It was a nice talk. I actually had a question on the LTO results. Can you comment on what the impact on the compilation time was with the LTO enabled?
So it depends on how big your application is, of course. There's actually some times when the compilation is faster, and that's only because when we do LTO, we don't link the device runtime every single TU, which takes some time. But definitely for like very large applications, especially ones that don't even need the LTO because all of the definitions are in a single TU, kind of like CUDA or whatever. It can impact the performance. It's usually about like 2 to 4 times as much for the large applications. But one of the benefits of this relative to host code is that there's usually much less device code than there is host code. So the overhead for LTO is, maybe I could have gotten some like more precise numbers, but it was never obscenely bad. It was always pretty reasonable.
Let's thank the speakers again for their awesome talk.